Okay, so I'm going to go through the example problem here for the sound intensity or the decibel problem. But let's just start off with a brief introduction. So if you can, if you just read here, you can see that that sound is important not only in aviation but in general. There's lots of regulations with regard to, noise pollution or care and concern about workers who work in environments, construction, other environments where the sound intensity can cause damage to someone's hearing and also disrupt sort of quality of life for people that live there. In aviation, there are certain abatement acts that were implemented, and really the purpose of those were so that there were standards put in place from airport to airport, and so you can sort of compare sound levels and set regulations and expectations. And what they do is they look at those levels on an average, so they adjust for day or night average sound levels. And so here's just the Abatement Act that was in 1979. And you can just read a little bit more about what that constituted. But down here, you see sort of the formula or the standard process that airports need to go through to actually define what the sound level is. So sound is measured in the pressure level in decibels. That's what dB, small dB is decibels. And what they do is they use one microphone location and they record all the sound that's happening, right? And it, there's peaks and valleys. It's not constant sound. And they come up with this LEQ level. So it's a level that is averaged based on peaks and valleys. And you can see in comparison to the max level, there's a 10 decibel difference, okay? So then what they do is, if you look over here, I know it's kind of hard to read, but this shows an hourly change in sound levels at the airport. And so that's DNL, which is day-night level. And they average that sound level. And they also adjust it. The dark blue is they actually add a additional 10 decibels for nighttime sound because it's more disruptive. And then they come up with an average here. So you can see it has peaks and valleys here, depending on what the time of day is. And then they come up with the average of that level. So this number here would be sort of what they call the DNL level. Okay. And so I'm just going to scan down for a second to the next page and just show you. So you see here this DNL level and these sort of contours here. So this is an average day-night level depending upon where you are on the runway or throughout the airport. Okay. So let's go back to the example problem that I wanted you to sort of go by. So when we talk about decibels, so decibels are just a way to measure how loud a sound is. And decibel is measured or compared to some sort of reference value. So usually that reference value is like the softest sound that a human can hear. And so they take whatever the sound is that they're interested in and they compare it to this standard reference level I0, we're calling it. So we take whatever the intensity is of the sound in question, divide it by that reference level, take the log of that, and we multiply it by 10. This is equal to sound level in decibels. Okay, so if we look at our example problem here, it says that we have, actually this came right out of the textbook, right? We have a vacuum cleaner sound intensity and then a balloon popping, and we're calling that IB is the intensity of the balloon popping and IV is the intensity of the vacuum cleaner. And so what we're saying is that the intensity of the balloon is equal to 125 decibels. So using this down here, okay, 125 decibels is equal to 110 times log of the intensity of the balloon over that intensity of that reference sound, okay? And so then the intensity of the vacuum cleaner is 75 decibels, and we've got that indicated here. Okay, intensity IV is the intensity of vacuum cleaner divided by that reference level I sub 0. So now we're going to use our log properties. So we've just sort of translated 125 125 decibels is equal to this term here, and 75 decibels is equal to this term here. And we want to find the difference, how many times greater is the sound intensity of the balloon popping versus the vacuum cleaner. But because we have logs and based on our log properties, we can use that quotient rule for logs. So we're kind of going backwards. If you remember that if we had the log of m divided by n, we could write that as the log of m minus the log of n. So we're just going backwards. We have two logs that are subtracted, and we're going backwards and writing it as a quotient. So we have 10 log, and then we have this term is my numerator, IB over I0, okay, and IV over I0 here. So we're just doing some algebra then. If I have IB divided by I0 divided by the intensity of the vacuum cleaner divided by the reference, okay? If I don't want this fraction here, I can do kind of keep, change, flip, and this becomes this term right here, okay? So I get IB divided by I sub 0 times I sub 0 divided by I sub V. The I sub 0's cancel out, and I just get IB divided by I sub 0. So that's what I have there. Okay, that's just using log properties. All right. And so now I'm going to divide both sides by 10 as well here. Okay, that gives me 5 decibels is equal to the log of the intensity of the balloon divided by the intensity of the vacuum cleaner. And so if I take my log properties, remember if I have log of x equals y, this is base 10, right? We know this is log base 10, so I can say 10 raised to the y equals x, right? That's all I'm doing. This is log base 10. So in this case, 10 raised to the 5th is equal to the intensity of balloon divided by the intensity of the vacuum cleaner. And then I just multiply both sides by I sub v, all right? And I get 10 to the 5th times I sub v, the intensity of the vacuum, equals the intensity of the balloon. So the intensity of the balloon is here 100,000 times the intensity of the vacuum cleaner. So you're just using that same thing for this here. So we are interested in the intensity on the inner runway versus the outermost runway. So if I had 75 decibels minus 65 decibels, we want to set up that same log. So for instance, log of the intensity of the inner runway divided by our reference. Okay, so then just follow along that other example problem. And then if you go down to this next page here, here's actually, you can see that I sub 0 here, 0 decibels is the weakest sound heard. So they're just taking sort of this scale here and they're dividing sort of by this reference decibel, which ends up in our example, though just canceling out, right? You saw in this right here, it in the end, because we're taking the fraction or the ratio of those two, that reference decibel cancels out.